Yes, sir, here.
Yeah. Hello.
Yes, yes, I wanted to ask whether you plan on taking a quiz or something in the near future.
Yeah. That's why I was trying to tell you what I have been planning, and it's good that you raised this point before I started talking about it. Huh? Okay. I am thinking that what about next Monday?
Yes, I will do.
Yeah, it's okay, right? Next Monday.
For quiz?
Yeah.
Yeah.
Yes, sir.
Okay. So, this the TA will inform you in details how we will conduct the quiz. Everything you will be seeing through your this WhatsApp group. Okay. So, sometime of tomorrow we will address this point, or later part of this week. So, let us fix it on Monday, and then of course it's the 10 marks followed by 40 marks our NSEM exam, or whatever you say. So should I begin, or I should wait a little bit more?
You can wait 2 minutes.
What are you suggesting me?
Maybe you can wait 1 or 2 minutes. More people will join.
Right. So just 15 students have joined, or 14. So I can see now. So you have no problem in accessing the videos and your PPT, right?
No, sir, no problem.
Okay. How many of you are planning to move to? These are all 4-year BS program, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, today let us move into the other mechanism, which is called inner sphere mechanism. Okay. Now, to understand the inner sphere mechanism, you need to also recapitulate the outer sphere mechanism. There you have noticed in general, the primary point is there won't be any bond between the that is the primary difference you will see between outer sphere and inner sphere. That outer sphere, there won't be any bond between the reactants, that means oxidant and reductant, but they will come closer at the activated state, and there you will see the electron transfer at the precursor to successor complex, and then the dissociation takes place, right? And we have also talked about that in general, outer sphere is much slower compared to the inner sphere mechanism. And if you have a new reaction, you do not know in the beginning whether the outer sphere or inner sphere. So one of the riders to suggest in a prima facie, I'm not saying in a very conclusively, that if the rate is relatively slower, then it is a likely situation of outer sphere. Of course, not necessarily, but that's a general trend what we see in normal codes. Okay. And then when we talk about this outer sphere, we have the self reaction and also the cross reactions, right? Now, self reactions, you know what is the meaning of self reaction? That both oxidant and reductant, it is the same component, and which is rather difficult to follow because the same metal, same ligand, same geometry. Only your variation is the metal oxidation state. One will be oxidized, other will be reduced, and the question comes actually anything is happening or not. So one could follow it through the isotopic leveling, and which takes you beyond any doubt that yes, it is the real electron transfer takes place over there. But there is another way, aspects over here, the cross reaction. Cross reaction is not a problem. You have noticed the two different things are there. And if you go for a cross reaction, one of the guiding factors of the whole thing you have noticed, that is the difference in potential between the two component, oxidant and reductant. And which one would be the oxidant and which one would be the reductant, that depends on their relative redox potential. If one compound needs to oxidize someone, that means that compound, that oxidant itself will be reduced, that potential would be higher than the other component, otherwise it cannot reduce. Vice versa for the reduction case. Okay, so that difference is very important. So and then there was a great approach by Marcus to figure it out, the cross rate, the reaction rate under the cross situation. And there you have noticed that very simplified equation, though the equation itself is very complex, but there is a very simplified form to understand from the inorganic point of view. And there we have noticed that equation contains that self reaction rate. That means any cross reaction having the two self reactions, and the self reactions rates for both the reactions, and the equilibrium constant of the your cross reaction. Now, self reaction rate that you can individually calculate based on that some your experimental features like ESR and NMR and all these things, one can determine it. And then you can put it over there, and the K of the cross reaction you can back calculate based on the difference in potential and the Nernst equation. Already we have discussed all those things. And once you get the capital K, that means equilibrium constant of the self reaction and the rate of equilibrium constant for the cross reaction and rate of the self reaction, considering the fact of the F factor in that equation 1, you will be getting the rate of the cross reaction, and that also you can determine it experimentally, and it matches quite well for many cases. But in certain instances, you would be also seeing that the calculated value won't match with the your experimentally observed value. Then the question appears, the validity of this approach. Okay, that is the standard mode of moving experimental thing. So then Marcus figured it out, what could be the probable factors which did not allow the calculations to reach closer to the experimental in those instances. Okay, and then he came up with a certain understanding, and which seems to be very logical. That there are a few points, that one of the points was that activation process for the independent of each other. That means you have two self reactions which are giving you the cross reactions eventually, and there some pre-assumption was imposed which are not quite fitting on all occasions, and if it does not fit well, then your consideration of coefficient of that F1 which does not stand, and that could be one of the factors for which your deviation may develop. Another important factor he talked about, that if the potential difference between the oxidant and reductant, which individually you can experimentally determine by electrochemistry, particularly polarography or cyclic voltammetry, and if the gap or potential difference, that means delta E, is too low, that could also contribute towards this difference between calculated and experimental values. And one more point also, important point raised, that if the reaction is not completely, following the outer sphere, a certain percentage of inner sphere component is there, then suddenly it will not match. So that means, this inner sphere, outer sphere, when we talk about, we need to be extremely careful. Okay. There is a zone which is 100% confidently you can say that this is inner sphere. No question of any doubt. And there is another zone which you can consider in 100% sense that it is outer sphere. But you will always have a kind of thin line for the intermediate positions, where it could be outer sphere, could be inner sphere, or could be a mixed situation. So that is how it is saying that calculation, the way it is being considered to calculate the cross reaction based on the self reaction, that is important. And if some percentage of inner sphere pathway is involved, then naturally calculated value won't match with your experimental observed value. Another process it says, and that already we have talked about, the cross reaction, or outer sphere, any outer sphere rate is lower. Okay. Now if the reaction moves very fast, okay, then certainly it is not following the outer sphere mechanism. And when a reaction can move very fast, if the delta G is very, very negative, okay, very spontaneous reaction, there it has to be. So these are intuitive. Okay, you cannot say this one is that and that one is that. All are mixed together. So one has to understand the process in a collective sense. Okay. Now, and then this is one of the examples I think I have discussed last day, that this reaction one can think about in a outer sphere, simple outer sphere way also. That is not a problem, because this is not the usual way to form the bridge. This is the acetyl acetonate, and normally acetyl acetonate does not form any sort of bridging, any sort of bridge with the incoming groups. But in this case, crystallographically they have showed that it has outer sphere component 31%, where there is no bridge. Okay, but there are two more states are there where it can bridge, though weakly, and you could notice that these are all dotted bond, not the solid bond. That means very weak, but it is not negligible. So you cannot neglect it. So you see that this is called doubly bridged and this is called singly bridged. So these are the components which are responsible for the inner sphere mechanism. Because inner sphere mechanism, unlike the outer sphere mechanism, the bridge is one of the important component over there. You have to have the bridging over there. So the whole reaction, these are experimental fact. This is not the case of any assumption. Okay, so they have noticed that these reaction where the calculated is a cross reaction, and not the self reaction. So these reactions, where your calculated values deviate severely from the experimentally observed value, and they tested and they could figure it out experimentally that here you have the two bridging mode. Crystallographically they have shown it. So their final conclusion is only 30% is your outer sphere, falling outer sphere mechanism, whereas rest 70%, okay, following the inner sphere mechanism, and that causes the difference. Now what happened? Then they have developed many such series where the things are not being following properly, and then they noticed that outer sphere component is also associated with the inner sphere component in a different percentage. Okay, here it is one of the extreme cases where 70% is your inner and 30% on the outer. Okay, but in that there are cases where you might have say 80-20, 70-30, 60-40, all sort of ratios are probable over there, and one could establish it even experimentally by simple crystallographic features and other spectroscopic features. Now, if you move to and then all sort of things we have already discussed. Now, if you move to inner sphere mechanism, so one of the important components of the inner sphere mechanism is that there should be one bridging ligand between the oxidant and reductant. Now, if we talk about the presence of a bridging ligand, then that raises variety of questions. Okay. Now, if all ligands cannot form the bridge. Okay. If any ligand needs to form the bridge, it should have electronically rich feature, and it should have some kind of additional electron density which could be shared with the incoming other metal fragments. So a lot of things are involved in it. And once the bridge is formed, that means that there is one group which connecting the two metal ions, and then as far as the electron transfer is concerned, you can expect to have a super exchange pathway. Okay, and that again, we write for our own understanding with the solid bond, etc. But actually, there is no question of bond in the real sense. Okay, it is actually the overlapping of orbitals. That is very important. Remember that. Yeah. Okay. Now, if we begin with that, there are two compounds, right? You look at, this is the oxidant and this is the reductant. Now, deliberately, when you choose this example, that in this case, one X group is attached, both are octahedrally surrounded, right? In both the cases, one is the M, another is the M prime. Metal is surrounded octahedrally, all are monodentate ligand. Let us assume for the time being, not necessarily always you need to have monodentate. Okay, you can have also the bidentate. For example, this is the case where we have talked about, you see that bidentate ligand that can also form the bridge. Okay, but normally monodentate is better to understand easily. So that's why I have considered one monodentate ligand, and which is defined by the term X. Okay. Now, when oxidant and reductant would come closer, okay, under a particular chemical situation, then this X will form the bridge between the M and N prime. That's called the bridge. Now, the question is, M prime is already hexacoordinated, so it cannot go to the 7th coordination mode, because 7th coordination mode already we know that it's not a very stable situation, right? So one of the ligands out of the 6 ligands needs to be dissociated. So many steps are there. So that means this compound or this particular bridge or spacer, we call it sometime, that would push one ligand to get out of the metal field, and it will form a bridged complex. And if you look at, this is the pentacoordinated, this is pentacoordinated, and this is satisfying the 6th coordination for both the metal centers, and Y is getting off the system, right? Now, one could have argued also that this X could have been dissociated, and one of the Y could have function as a bridge. So everything depends on the factor, the electronic situation of X and Y, or L, X, and Y. Okay, there are 3 ligands, 3 types of ligands are there. The best electronically rich, the best item will form the bridge. Now here we have assumed that X is a better bridge than L and Y. That's why it is functioning as and this impact is so strong that one of the Y's, it goes out of the coordination sphere. So you will have this, what we call it precursor compound, where there is a bridging situation, and that was never present in the outer sphere mode. And then what is happening, and then you can have a rate of association, dissociation, all sort of things. And then once it comes closer, then you will have the electron transfer between M and M prime. So M would be reduced and M prime would be oxidized. And do not forget that similar activation barrier would come also here. That means your bond angle and bond distance, all sort of things would be changed while moving from this side to that side. And that requires additional, your activation energy, like outer sphere. So that will be operational over here. Now, after this, when this, after electron transfer, now what will happen? You have started with this, and then your product would be not the bridged one. Product would be the oxidized and reduced mononuclear compound, right? Because you have not started with the dinuclear compound. Here you have assumed a dinuclear compound. I should say the bridged dinuclear compound as an intermediate. Okay, so after electron transfer, then what will happen? The dissociation will take place. Now there are a couple of questions. Now dissociation will take place at what point? After the dissociation, X will go to the M prime part or X will go to the M part. That is a debatable question, right? Now, if we assume for the time being that X is going to the M prime, then the product would be X M prime Y5, right? And this Y, which is already present in solution, will come and attached over here. Alternatively, one could think about this X would come in the domain of M instead of M prime. Then your product would be L5MX, what we started with, and then your M prime would be Y6. Only variation is we started with the 3, and this is 2, and this is 2. This is the net electron transfer. But in this case, there is no ligand alterations. But in this case, electron transfer followed by ligand alteration, which have been taken place. So I have raised many questions over here. One of the questions, the first question is that out of available 3 ligands, forget about the metal, available 3 ligands, which one could function as a better bridged? That depends on the nature of L, X and Y. Nature in terms of the electronic nature. We will explain all these things. Now, since you have assumed X is the better fitting, and that's why X is forming your bridge over there. Once that is being formed, and then the reorganization in terms of bond stretching, bond vibration, that would take place with the available activation energy in the system. And then electron transfer will take place. That M will be reduced from M3 to M2, and simultaneously M3 will be oxidized from M2 to M3. But that is not the final product. That is the intermediate product. And then the dissociation will take place. Now when dissociation will take place, then the bridge needs to move into one direction, either M direction or M prime directions. And based on that, the product distribution will take place. And accordingly, the available dissociated Y, what happened in the initial stage, that will get linked to one of the metal centers. Now, whether X will go this direction or that direction, that depends on the inertness and the levelity of that particular compound. Okay, that particular mononuclear setup. Inertness and the labile feature. You could remember that before starting this electron transfer, I had shown one slide where we have talked about little bit about the labile and inert situations, which electronic configuration could be considered as inert and what could be considered as labile. In octahedral situation, similarly, you can think about in other geometries. So whether X will remain attached or associated with the with the initial M, or it will move to the M prime. Everything depends on the inert and labile feature of this. We'll explain it now. And again, inert and labile feature of M or of that mononuclear unit, that depends on the fact of the electronic configuration of that particular M in that particular compound under that particular geometry. So many things you have to consider together, and the spin state also, high spin, low spin, and all sort of things. Now, if you take this example, here what we are showing, sorry, yeah, just a second. Yeah, if you look at this case, what we are showing, that cobalt hexammine, which is reacting with the chromium hexammine, sorry, chromium hexaquo, and the product is okay. Let us first assume in the beginning that cobalt 2 hexammine and chromium 3 hexaquo. Okay, and this amine is replaced by water. I will come later on. Okay, now what is happening? This reaction, and if you look at the rate, and rate is essentially suggesting is an outer sphere mechanism. It is not following the inner sphere mechanism. You could argue that how do you come to the conclusion that it is not the inner sphere? The conclusion is very clear that 10 to the power minus 3, this rate is very slow rate. And inner sphere rate, normally it is not go by that slow process. Okay, outer sphere could be also, rate could be faster, but normally such a slower rate, it is an indicative of or indication of the outer sphere thing. Now I could argue that why it is outer sphere, the rate is just the prima facie information. But if you look at the ligands over here, amine and water, none of the ligands could be considered as a good bridging ligand. And more particularly the amine, there is no excess lone pair over there which could share with the neighboring other metal centers. Now oxygen, one could imagine to have some amount of your bridging power because it has one extra lone pair, but that's not a great bridging ligand. Very few compounds you would see where oxygen is forming a good the bridging ligand. Not really. So considering all the facts together, what one could imagine that this is essentially an outer sphere mechanism, and the reaction rate is also an indicative in that directions. Now the next question is why it is being written cobalt 2 hexaquo instead of cobalt 2 hexammine. It should be cobalt 2 hexammine. Now what is happening, if you look at cobalt 3 hexammine, it is octahedral, so T2G6, so it is inert, right? And chromium 2 means T2G3 Eg1, so it is labile. Now, when it is getting reduced, cobalt 3 to cobalt 2, that means it is moving towards the high spin configuration. And this is the configuration, it is now labile. Whereas if you look at this one, it is now chromium 2 to chromium 3, so T2G3, it is now inert. Okay, so what is happening? This reaction is being carried out in aqueous medium, so it is a labile. As a result, water is getting, this compound is essentially getting hydrolyzed. That means cobalt 2 hexammine initially formed, and that is getting hydrolyzed to cobalt 2 hexammine. And why it is getting hydrolyzed? Because of its labile feature. Because of its labile feature. And here nothing is happening because you have taken the aqua compound itself, and the medium is water. So it will remain like that because it is labile, but it cannot be replaced by anything. But here it is amine and it is water, so that could be, it is known that the amine compounds could also be hydrolyzed if the metal coordination, metal electronic configuration supports the labileness. Okay. Now if you go for this particular reaction, where deliberately you have used one chloride group. Instead of hexamine, you have used pentamine and chloride. Okay, and chloride is a very well-known bridging ligand. Everybody knows that chloride can bridge between the two metal centers without any doubt. Okay, now if you do this reaction over here, you look at first the rate. Rate is 10 to the power 5, and this and the same reaction, more or less similar reactions, right? Except one amine, you have taken the chloride, and rate has been increased from 10 to the power minus 3 to 10 to the power 5, and that gives the immediate impression that it must have been following through the inner sphere mechanism. Okay, now you have to first justify it, then prove it. Okay, that is the very subtle and delicate issue. You have to justify it, why it is not outer sphere. One of the impression is that your rate is much faster. That gives you an immediate impression, not necessarily correct impression, immediate impression. And then if you look at the oxidant and reductant feature, that oxidant, you see that one chloride is there, and then it is likely to be functioning as a bridge. Okay, and then the products are same. You look at the products are same. Okay, now there is one question comes over here. Another question, that this chloride is getting shifted to chromium, and then this is hydrolyzed. Now why it is hydrolyzed? Okay, because of this, it will form the amine compound in the beginning. Then because of the labile nature, like before, it will be hydrolyzed. Now chromium is going over there. Now the conclusive, evidence of inner sphere of this reaction, which has come out of the, structural characterization of the intermediate. So one intermediate could be also isolated and crystallographically characterized, and that showed that essentially this chloride is bridging between cobalt and chromium, and as usual, to bridge one of the Y groups would need to get out of the system, and that is being happening as pentaaccio instead of hexaaccio. Otherwise, it will become 7 coordinated, and which is known to be an unstable situation. So you will have the chloride bridge. This is a conclusive proof. First point. Second point is that once this compound is formed, then the next step is that after electron transfer, the dissociation has to take place. Now, let us assume the electron transfer has already been taken place over here, and then where the chloride would go? Chloride could be written over here, chloride could go over here, right? Now, if you look at the cobalt situation, after electron transfer, it's a labile situation. And whereas this is the inert situation. So naturally, this bond would become stronger compared to this one, because this is a labile situation, right? So this chloride would prefer to be associated with the center, which is considered to be the inert situation. And that's why instead of retaining with the cobalt, it goes to the chromium center, and then it could initial product would be pentamine water. One water goes in, one the chloride goes into the chromium domain, and then all amine would be hydrolyzed by water, and so you'll be getting this product, and you will be getting this product at the chromium part. But that is the ligand exchange process. Okay, that is the ligand exchange process. But the electron transfer is essentially happening at the metal center. So remember, one statement I made while talking about the outer sphere mechanism, that there won't be any ligand exchange. Okay, only the electron exchange between the oxidant and reductant. That because of the fact the electron transfer thing is much faster than the ligand exchange. Okay, and here what happens, because of the bridge, already there is a bridge. So your ligand exchange is a likely situation, and then inert and labile feature, then hydrolysis is one of the common factors. Now again, you can put up one more question, that this chloride might have come at the final stage. The chloride might have come from the solution. Solution might have some amount of chloride. Say if you are taking water, water contains some chloride anyway. So it could be the part of that chloride, not the bleached chloride. Then they have also performed the control experiment by using your if we use these at start and add your label chloride in this mixture. So what you are doing, the same reaction, you are adding label chloride in the mixture, and you will see very minimum incorporation of the label chloride over here. Or otherwise, if you use this one as the labeled one, you will see the labeled one over here. And if you don't use the labeled one over here, use the labeled one externally, you will see negligible incorporation over here. That means this chloride is essentially the part of this bleach, not coming from the solution. Okay, and that supports the inner sphere mechanism to a large extent, that here it is essentially proceeds to the super exchange pathway through the formation of a suitable bleach. Okay. Now, if you put all these things together, there are few points. Let me put it one by one. And anyway, you will get the slide and you will see it little carefully later on. It says that ligand which bridges two metals is primarily involved in the electron transfer process. That means the electron transfer is happening between the two metal units, one oxidant, one reductant. Oxidant is getting reduced and your reductant is getting oxidized. That means reductant is transferring the electron to the oxidant. That's it. But how it will happening? In this case, it is happening through the bleach. Okay. How it is happening? It is happening because of you have the orbitals of this d orbitals over here, d orbitals over here, and the chloride having the p pi star orbital. So the p pi star orbital over here would overlap with the d orbitals, and this will overlap with the d orbitals, and then you will have the pi cloud over here and pi cloud over here, and by that process electron would transfer either through tunneling or through hopping process. Okay, that is the standard mechanism, which is called, I said, the super exchange mechanism. Okay, first the electron, both the electron will come, or the one electron which is getting transferred from chromium 2 to cobalt 3, that will come at the pi star level, and then it will be shifted. The second point is the bleach dinuclear clumpage is formed by sharing one common ligand. That we know already, na? A net electron transfer from Mn plus to Mn plus 1, that means chromium 2 to cobalt 3. Okay. Then success depends on many factors. Which are the factors? First is chloride firmly attached to inert cobalt 3 in the beginning. Displaces one water from the labile chromium 2 to form the bleach compound. This is very important. The first slide I have shown that in order to form the bleach with this reductant, one of the Y needs to be getting out of the system. Otherwise, no vacancy would be created where chloride or the X could breach. You have to create the coordination vacancy over there. Okay. If there is not suitable coordination site, then there won't be any breach formation. That is very important. Secondly, electron transfer takes place from this to this, leading to chromium 3 cobalt 2, and it gives inert and labile this. So chloride goes to chromium 3. That is important. Already I have talked about that this bleach chloride will not move into the cobalt 2 site because that is labile now. It will prefer to move towards the chromium 3 site, which is D3 configuration, T2G3, which is inert. And this labile, cobalt 2 pentamine labile picks up on water to give you this thing, followed by complete hydrolysis to give you the hexa aqueous species as we have talked about. And chloride is transferred to chromium through the bridge as the use of free isotope in solution. Very little level of chloride is detected in this phase. That means it is saying that chloride is coming through the bridge, not through the your solution. If solution, always you may have little bit chloride, okay, and it is not that chloride. That is very important. Now in this context, you see that I made a statement: the solution always may have little bit of chloride. You must have noticed in your +2 level or even first year laboratory that the tap water what we use, which contains a lot of chloride. Okay, that's why in the lab, instead of using tap water, what do we use it? We use the distilled water, and sometimes we also use the double distilled, millipore, all sort of pure water. Pure water in the sense there is no chloride in the situation. Now the tap water contains chloride. How do you prove it? Could you imagine how do you prove it? It's a very simple test. The tap water, any tap water if you take, and I'm telling you that chloride is there. So tomorrow when you will back to IIT and you will be doing any lab reaction, you can prove by yourself that the tap water contains chloride. You just take a pinch of silver nitrate, okay, AgNO3, and put it in the tap water. Immediately you will be seeing that white, coagulation, colloidal type of white particles. What is that? That is essentially silver chloride. Okay, but if you take filter water, you will have little bit chloride also. But if you take that millipore or finely distilled this water, then you will see there is no chloride into it. Now that why I am mentioning this point, that always you will have the probability to have some amount of chloride in the whichever way you try to purify the water, and during the course of the reaction, if little bit chloride is there, that is quite good enough to replace one of the water molecules and to give you the chloride. Chloride is a stronger ligand in that sense, the anionic ligand. So to prove that, you have to use the isotopically labeled. Yeah. And if you use isotope by mass action, it would go over there. If it is really from the solution, because you will be taking higher isotopes. Nah? So the other one will be replaced by the isotope one, and it will go over there. But that kind of incorporation was not there. And you can also prove it otherwise. In the beginning itself, that cobalt compound whatever you have used, pentamine chloride, you can use the labeled over there. Okay, and let the solution be the normal chloride. So if you get the 100% labeled one or close to 100% labeled one into the product, that means it is coming from the bridge. Okay, but you will have always little bit ratio, not necessarily 100%, maybe 90-10, something like that. And 90-10 is quite good to tell that it is coming out of the bridge to justify your argument. Now again, you have to understand that earlier example we said that chloride is moving from cobalt side to your chromium side after the electron transfer. And the argument what we have given, the argument what we are talking about, that it is based on or as a function of inertness and labileness. So the chloride is moving in the direction of the inert side. That means initially there is a bond. Now it is a bond. Bridge means bond. So chloride is moving from towards the side where it will be inert. Okay, so more stable situation. But if you take this example, okay, after that example, that let us try the iridium Cl6 2-, that means iridium 4, and you are using, this will be the chromium, chromium 2 hexaacro compound. Now iridium 4 means T2G5, so it is labile, and chromium 2, which is again labile. This is high spin, this is low spin. And the electron transfer, iridium is getting reduced to iridium 3, and chromium is getting oxidized to chromium 3. So this is high spin T2G3, this is inert. This is low spin T2G6, this is inert. Okay. Now you see there is no chloride exchange, though crystallographically one can prove very easily that chloride breached intermediate is involved in the electron transfer process. So chloride breach compound is formed, and then electron transfer takes place through the orbital overlap, as I have mentioned, the d pi orbital, and p pi star. Then the first electron from here, it will come over here, and then it will come here. So you will have pi cloud over here, pi cloud over here. And there is no chloride transfer. Chloride goes back over here, and no hydrolysis. Unlike the cobalt case, you will have the hydrolysis case, na? Hydrolysis case. And here, because why hydrolysis takes place? Because this is a labile product. Okay, so amine could be easily replaced by the water. Now, in this case, what is happening? That first of all, chloride is a better ligand. This is true, but still it can perform in the hydrolysis. Okay, it could be hydrolyzed, but it is inert, and again it is inert. So both the products, are inert. So chloride did not have any option or did not have any reason to move towards the other side. Earlier there was a reason. Instead of moving back to its original position of cobalt, it moved back. It went towards your new site, chromium. But here you see that it does not, gain any additional energy or stability, because both the products are inert. So it prefers to stay back over here. First point. Second point is you don't see any hydrolysis over here, as because of the fact the inertness of this thing. So inner sphere mechanism one needs to understand also from the point of view of inertness and the lability of that compound under that particular oxidation state and the spin state. Okay, you understood, na? Now if you move to another example, this is a very interesting example. You will see certain other important issues. You see, if you start with the ferricyanide, iron 3 hexacyanide 3 minus, and cobalt pentacyano water. Okay. Now, if you look at this iron 3, this is low spin. Cyanide is a strong ligand, so T2G5, and cobalt 2 pentacyano. So this is cobalt 2, so it will be high spin. Remember, most of the cobalt 2 compounds are high spin, barring only I think 1 or 2 compounds are low spin compounds are available. Okay, this is a very interesting point I am sharing with you. So remember that all cobalt 2 octahedral compounds are high spin. Whether you take monodental ligand, you take your chelated ligand, it doesn't matter. Under octahedral condition, always it is high spin, barring only so far. Globally, only 2 compounds are known where cobalt 2 octahedral low spin compounds are there. It is because of the CFSE. Okay, so you can back calculate CFSE and you will see huge gain between the low spin and high spin. So what I'm trying to say, that this compound if you start, then water will go up. As per our initial slide, water will go up. Water is a good living group. We know it. So do not try to forget basic chemistry ever. Whatever you learned in plus 10, plus 11, plus 12, everything would come into your use. You don't know why. So the water will go up, and then you will have cyano breached iron cobalt compound. Okay, and then your electron transfer will take place. So I have not shown the electron transfer in the breached form, but at the end, what is happening that this cyanide remains over here. Okay, instead of going over here, and here in both the cases, your products are inert. Now, if you try to understand this example and this example, there are certain fundamental points out there. What are the subtle differences between the two situations? Here, chloride is your bridging ligand, right? And chloride, this phase and that phase, there is no difference. It will always, chloride will link to the metal, either with the chromium or to the iridium. But cyanide situation is different. Cyanide is it can bind to the metal with the carbon or to the nitrogen. Both the ways it is possible. Okay. Cyanide, isocyanide, what you say, no? Thiocyanide, isothiocyanide, all sort of things are there. So what will happen? Now here both the products are, after electron transfer, both the products are your inert. So that way there is no preference like here. This is inert, so it prefers to move to the side where it was in the beginning. And here it moved in this side. We have one more argument why it preferred this way, because if it goes over here, then it will remain linked to iron side to the carbon. But if it needs to attach to the cobalt side, then the bonding through the nitrogen, which is not a very stable situation. I hope you understood it. So what I'm trying to say, that where the bridge having more than one donating site, then you have to figure it out the preference of movement, not only based on the fact of inertness or lability, but also based on the consideration of that which donation mode or which donating site would be a better choice in terms of stability. And again, you have to bring your earlier knowledge that if cyanide is a ligand, a carbon bonded cyanide is a stronger one compared to the nitrogen bonded cyanide. So in this case, it will move in this direction instead of in this direction. So these are the two examples which tells you that if it is inert, the chances of movement to the other side of the bridge is not likely. And also it tells that if you have a bridge having more than one donating site, then the stability of the particular donating site would be the matter of consideration in addition. Okay, so that you have to take into account. Now, if you try to see the energy graph, now when you talk about the electron transfer, our one of the primary goals is to figure out the rate of the reactions. Now, how to figure it out the rate of the reaction? So, rate of the reactions, remember, we calculate or we determine based on the fact of the slowest step. The step is the particular step which is the slowest one, that is called the rate determining or rate limiting step. Now, our how many stages are there here? If you look at the inner sphere process, first is the L dissociation, what we have shown. Then the bridging complex formation. Okay, L would be dissociating from one of the reactants. Then the breached compound would be formed, and then electron transfer would take place. Then bridge will be breaking, bridge will break. Okay, and then the L which was dissociated in the beginning, that would be getting associated with one of the products, and that is this. So there are two ways to think considering what particular reactions you are considering. So you have to see it. This could be the limiting step in in most of the cases, but in certain cases, this could also be the limiting state, okay, or the rate determining state. So inner sphere depends on the nature of the breach, as you have written. You look at, if you take the example of amine and chloride and hexamine, okay, what we have noticed, if we started with the hexamine, it is perfectly outer sphere. Yeah, this example, it is perfectly outer sphere. Slight amount of inner sphere might be there, but who cares? Mostly it is outer sphere. Why it is outer sphere? But as soon as you take, replace one amine by one chloride, and you see the inner sphere mechanism, right? So why it is so? It is says very clearly that the rate would be 10 times faster for this case, because amine has no additional lone pair to bleach the other metal. Okay. So what we are trying to mean is chloride the best bridging ligand? Answer is certainly no. Chloride is one of the effective bridging ligands, I should say. Might not be the best, but it depends on many factors. One factor is the bridge could be your neutral. Neutral means it has to have the additional lone pair, okay, which could be shared between the two interacting metal ions, or the metal ions which are participating in the dinuclear formation. Or bridge could have your anionic charge. Chloride is of that example, that it is anionic, so it can form a nice bridge. Or you have to think about, there are many anionic ligands, okay, and all can form the bridge, but all are not the best. Now, which one would be considered to be the better one based on the extent of the polarizability? That means if you increase the size of the bridge, okay, then polarizability increases. For example, among the halides, and you already know it, that if you go down from fluoride to iodide, the size progressively increases. And there you see that your iodide, which facilitates the electron transfer process to a larger extent. Look at this experimental data. You will see it. Now we are considering the same reaction, cobalt pentamine X plus chromium 2 hexaco. Product is cobalt 2 hexaco and chromium 3 hexaco, right? Now this X you are varying, okay. Now X, what you are doing? You have started with the amine, you have then started with water, then azide, then hydroxy, fluoride, chloride, bromide, iodide. Now, after that, you will be only getting the, if X is hexamine, right? You can only determine the rate, second order rate, right? Okay. And when you are determining the rate, it will never tell you, I am outer sphere, I am inner sphere. It will never tell you. You have to judge it by considering the factors of how slow the rate is and how fast the rate is. So that will be your, initial impression. Not necessarily always you are correct, but once you have the amine, already you have discussed that amine cannot form the bridge, and if bridge cannot be considered towards the understanding of electron transfer of that particular reaction, then what alternatives we may have in hand? We have only one alternative, that is outer sphere alternative, and that is indeed being following over here. Now if you go to water, as I said, water is a better candidate for bridge than amine, but not a good candidate. We will be very careful. Well, for example, sometimes I say that one student is excellent. That's an exceptional case, we keep it in one side. Other student very bad or very weak, so you keep it in the other side. Now you have in between a student who are, so-so, say not good, not bad. How do address that situation? You cannot say bad because they are not bad. On the other hand, you cannot say good. I'm talking about in terms of the intellectuality. You cannot tell them good because they are not good. So somewhere in between, right? So water is a case where you cannot say that it cannot ever form any bridge. There are some examples where it can form rather weak bridge. Why it can still form weak bridge? Because it has one additional lone pair. But the amine does not have any additional lone pair. One lone pair that is shared already with the first metal ion. So water could be considered as a probable bridge, not necessarily a good bridge. And you look at the rate is an impression of that, right? It's not a good bridge. So water also, will take you towards the outer sphere pathway. Now, if you look at azide, immediately your rate is increased to 10 to the power 5, huge. Okay, and it is good point is it is symmetric in N, and other point is it is anionic, no problem. Hydroxo is a very good bridging ligand. All of you know. Look at the rate, and then halide, look at the rate. Okay, so rate is progressively increased downwards. So why it is progressively increased downwards? Because of the fact that polarizability. Okay, how the orbital would be disposed around the bridge, how it would interact with the metal d pi orbitals, and what extent of covalency and what extents of overlapping would take place, that depends on polarizability, size, charge, all sort of factors together. And this is being very nicely reflected in this particular thing. So among under the banner of inner sphere, so bridge is one of the very, very important aspects to follow the reaction rates, kinetics, and all sort of things. Now, if bridge is so, this is the same slides we have already talked about. Now, another thing, this is very important. Now, when electron transfer takes place between a particular pair, then electron transfer, it could take place through the pi root or through the sigma star root. For example, the sigma star root, it depends on the, say, if you take, these are the, chromium 2 and cobalt 3, this is the pair. Now, first consideration is homo sigma star and lumo sigma star. Okay, that means that in this case, this is the sigma star Eg. Eg is the sigma star. Now, chromium 2, if you look at, this is the electronic configuration, and cobalt 3, all octahedral situation. Cobalt 3, this is your, sigma star situation is vacant. So this electron transfer, if any electron transfer takes place, what will happen? It will take place from sigma star to sigma. Now you could remember in the outer sphere time, we already said the electron transfer between the oxidant reductant, it does not take place haphazardly or randomly. It takes place by following the symmetry of the orbitals. So in gist, what I said, that it will prefer to take place between E to E or T to T. If it happens directly, no problem, or it will follow the via media. I have shown on slide, it will follow the via media to have that tendency. I think you could remember this slide. Yeah, this route is not allowed. So it will follow the via media. Okay, I've already talked about it. So the symmetry guided electron transfer actually. So that's why it says if it is sigma star to sigma star, that means this is sigma star, this is sigma star. So this electron will go over here. That's why cobalt 3 will become cobalt 2, and that rate is very high. But remember, it is not outer sphere. It should be inner sphere, because what will happen here, if it is outer sphere, then it requires a lot of reorganization energy over here. Why? Because cobalt 2, when it will form cobalt 2 after electron transfer, it will become high spin. So low spin, high spin, reorganization, all these things, but this electron transfer will be fast. That means it will prefer to follow the inner sphere mechanism. Alternatively, the next one is sigma star pi star. Another way, sigma star pi star, that means again this will come to here. Before that, the one vacancy has to be created. That means first it will go to the your high spin configuration, followed by electron transfer. So too many hodgepodges, and you look at the difference, 10 to the power 10 to 10 to the power 2. That means this option means then it will go to the high spin. That means your 1, 2, 3, 4, 5, 6, 6, 1. Then vacancy is here, so it will come over here, and which is symmetrically forbidden. Not forbidden exactly, but not preferred, and that is being reflected in the rate. Then other option is pi star to sigma star. That means from here to here, pi star to sigma star. And this rate, again, which is not a preferred situation. So that is being reflected over here. And if it is completely pi to pi, that means all these steps, this is 100% inner sphere. These are preferred by the inner sphere mechanism. But if it is taken place from here to here, that has to be completely outer sphere. That means rate will be very slow over here. But the same situation, you will not see why sigma star. You see that these are the overlapping mode I was talking about. The metal d orbitals, here it is x square minus y square, x square minus y square, and the ligand sigma. That means this is sigma orbital, this is sigma orbital, and the ligand sigma, they can so nicely overlap. That's a sigma star as it is being shown. And because of this strong overlapping, you can see the rate is so high over here. Okay, and that means it is the inner sphere mechanism. Okay, and if you go to chromium and ruthenium example, then what will happen? That reorganization factor won't be that prominent, because it will remain ruthenium 2 and ruthenium 3, both are low spin. So this is a different situation. Again, the same situation over here. You will have reorganization factor over here, and in this case there is no reorganization factor either here or here, and as a matter of fact it will be completely outer sphere mechanism. So what I am trying to mean only out of this, that sigma star is the preferred overlapping zone, but you cannot help yourself all the time. It depends on what particular oxidant and reductant you have chosen. An oxidant reductant you have chosen based on many other factors, the compounds, what you have in hand, what is your actual goal, what you want to do out of this reaction, what you want to understand out of this reaction. So keeping all these factors in mind, you have chosen oxidant and reductant. So your option is also rather limited over there. And whatever oxidant and reductant you have chosen, and there you have to see that unpaired electron, it is available in which set, sigma star or pi star, or vacancy is where sigma level or pi level. And if you use one bridge, then that is additional factor. So taking all this into consideration, sigma star is the best option, followed by the other options what it is being shown over here. But if you take additional reorganization factor in it, that means in case of cobalt, one has to be very careful that that cobalt 3 high spin to cobalt 2 low spin, lot of reorganizations of electrons between the T2G and EG, and that requires a lot of additional energy, and that might retard the process to a large extent. and there you may go for the inner sphere preferably. Now you also see that if we accept the fact that breach is one of the, or probably the most important factor as far as your inner sphere electron transfer is concerned. Okay, then there are several factors you need to take into account around the breach. Now look at this particular reaction, very simple reaction. What you have done, you have taken cobalt pentamine, cobalt in the 3, and you have taken this acetate bridge, RC double bond O, and you are taking chromium 2. Product would be very simple. It looks very simple, but it is very delicate. Electron transfer looks simple but delicate. So one has to understand with a lot of patience. Now chromium 2 is getting oxidized to chromium 3, and cobalt 3 is getting reduced to cobalt 2. Okay, and this is the bridging mode. You look at that acetate, that O minus bridged to the cobalt side, and then double bond O is bridged to the chromium side, right? Now what might happen, not necessarily that if you have the structure of the intermediate, it shows that this is not exactly double bond, this is not exactly single bond. Basically, this is the intermediate. This double bond is then delocalized between the two oxygen centers. That means it will be 1.5, 1.5 bond order. Okay, not 1, not 2, 1.5, 1.5. So the way we write now, we write this way, and minus is over here. But it doesn't matter, it's a mononegative ligand, and that will bridge with the chromium 1, and then this chromium having water over here, then inner sphere standard route it will follow. This is the electron transfer route, okay, and it will be reduced, it will be oxidized, and that is happening. Now, if you determine the rate of the reaction as a function of the R, deliberately they have considered the R different. In one case, R equal to H, R equal to methyl, R equal to phenyl, R equal to T-butyl. And if you look at the rates, second order rate, it is decreasing. Continuously it is decreasing. Starting 7.2 to 0.35 to 0.15 to -1. That means what is happening, that as you use the bulkier R, that retarded the electron transfer rate or the overlapping. It is being reflected in the rate. Rate is being decreased while moving from H to tertiary butyl via methyl and phenyl. Rate is reduced. The question is why the rate is reduced. Rate is reduced because of the lack of effective overlapping. So overlapping taking place between this orbital, and this whole orbital over here, the pi orbital over here. And this overlapping won't be that effective if you move from H to tert-butyl. Okay, and if it is not that overlapping, then your super exchange between this domain would be not so good, and that is being experimentally manifested in their electron transfer rate. Okay. Now another point is also very important as far as your inner sphere electron transfer is concerned. You can recollect, I said that it is following through a super exchange pathway. That is not the case in case of outer sphere. There is no breach, no bond formation, no bond breaking, etc. But here, this slide is very important. Okay. Now, here it is a sigma interaction. It could have been also the pi interaction. It doesn't matter. But what it matters over here, it matters that how important the orbital is. Electron transfer, everything what we say for the sake of our one understanding, but it is essentially following through the overlapping of orbitals and electron density. Okay, how the electron density is being shuttling between the two or more interacting domains or interacting entities. Okay, and they collectively create one domain. Okay, and you look at this orbital and the bridge orbital, they are overlapping. Okay, and this electron transfer takes place. So electrons are moving from chromium here, chromium 2. This will come to the vacant site over here, and then this orbital is already shared with this thing, and then electron will go from this side to that side. It's just like water, the way it is falling from higher domain to lower domain. Nah? Okay, so there is a potential gradient. That is true. Everything is guided by the potential. There is a potential gradient between these three, and this is the direction which is the favored potential direction. So electron will first come over here, and then it will go over there. How do you establish it? That is how we are trying to believe it. But none of our these statements are way of believing has any meaning until and unless we establish it experimentally. Now, this is one of the examples. There are many such examples. I am giving you one of the examples which could be very, very interesting. Now, if you look at this reaction, now this reaction could be followed by this way. So pentamine and one pyridine is there, and then chromium you have hexaquo. So like many other reactions, it will go reduced and it will oxidized, right? And if you look at the rate of the reaction, 10 to the power minus 3. Again, I would like to reiterate the same point. The rate is giving an impression of having your outer sphere mechanism. So this is an outer sphere mechanism. It is following outer sphere mechanism. Now, for the sake of argument, I would say why it would not follow the lower sphere mechanism, inner sphere mechanism, because of the fact there is no suitable group attached to the cobalt side or chromium side which could form the bridge between the two metal centers. Do you see any suitable entity which could bridge between the two metal centers? Answer is no. Because pyridine cannot bridge between the two centers. If you put one nitrogen over here, that is pyrazine. Pyrazine can be used as a good bridging ligand. And amine, we know it cannot form the bridge. And then chromium side, water, we know it cannot be the good bridge. It cannot be bridge, I cannot say, but it cannot be a good bridge. So the option is there won't be any bridge. And that is being reflected in the slower rate. So one could confidently argue that this is going towards the outer sphere mode. Now, if you modify the like a little just, what we have done, we means what is being done, the same pyridine you have attached on amide group over here, CnH2. Okay, and same aqua product is again the same. Chromium 3, this one, chromium 2. So instead of this, amide group is here. And look at the rate. Now 17.4. And previous case it is 10 to the power minus 3. So one could argue that it is inner sphere mechanism, or it is moving towards the inner sphere mechanism. So it has left the domain of outer sphere mechanism. 10 to the power minus 3, so it has come to 1.7 into 10 to the power 1 or 17, right? So it has left that outer sphere zone and it has moved into the inner sphere zone. Why it is so? Because of the fact you have now used one component at the para position of the same pyridine bridge, which could function as a potential, bridging group, and that is happening over here. Okay, first point, and it is being proved crystallographically. Yeah, that there are 6 water molecule attached to the 5 water molecule attached to the chromium side. So it's a nice bridging component is there. Second point I said, in order to justify that this statement is correct, the first electron will come from here to here, and then it will go to here to reduce cobalt 3 to cobalt 2. Okay, is it true? Yes, it is true. This is an example. What they could argue that final product is this will be cobalt 2, and this is fine. By mistake, it is cobalt 3. You know what they have done? They could isolate the intermediate. I'm sorry, not isolate. They could trap the intermediate. And at the intermediate, what they have noticed that this is chromium cobalt 3, this is chromium 3. Again, there is a mistake. This will be chromium 2. Okay, this is chromium 2 like this. Only they have shown the, no, this is fine. This is fine. This is chromium 3. Then it is getting oxidized, and the electron goes into the bridge over here. Okay, that is the intermediate state, and then this electron will come over here, and it will reduce it to cobalt 2, and it will be dissociated here to chromium, dissociate to chromium as chromium 3 plus. And how did they figure it out? You can figure it out the presence of this radical by trapping this molecule with the spectroscopic technique. So let me explain it once again. What is happening? Your starting is chromium 3 and cobalt 3 and chromium 2. And chromium 2, this particular ligand in one end, it is bridging to cobalt to the pyridine nitrogen. In the other end, the amide nitrogen is linked to the chromium 2. And then you have one intermediate is formed where this chromium electron is moving from here to here. Okay, and chromium is getting oxidized, and this group is getting reduced to form a radical over here, and this remains 3 till. So these are 3, 3, and the radical is over here. And then this electron is moving from here to here, which reduces cobalt 3 to cobalt 2. By mistake, it is cobalt 3, it should be cobalt 2. And chromium 3, which is getting off the system. And that means it is getting oxidized and it is getting reduced to cobalt 2 via the intermediate radical formation. Okay. And this electron transfer can happen through the two routes. We know that hopping method or through the tunneling mechanism. So that conclusively proves that it is passing through the super exchange path. The exchange is happening. Exchange happening between what? Between the two metal orbitals and one ligand orbitals. So the reduced metal transferring the electron to the bridge, and bridge is transferring the electron to the metal at the other side. Okay, it is just like the relay race. The way we transfer the button from one hand to other hand. Okay, now there are 3 persons standing, and the distance between 1 and 3 slightly longer than their summation of their hand distance. So if someone stands in between, then we would give it to the intermediate one, and intermediate one would pass on that particular one to the A, person A. Okay, so eventually electron is transferring from chromium to the bridge to the metal on the other side, and that is how the super exchange pathway functions. Now, how do you distinguish if electron transfer is outer? This is the question we have been raising last so many slides. Our full discussion is in that directions, right? So you have outer sphere route in one hand, we have inner sphere route in other hand, and we are debating that whether the reaction is truly outer sphere, truly inner sphere, or reaction is somewhere in between, right? And what are the complexities one might face in defining the electron transfer mechanism, and how one needs to address the complications and the delicacy between the two mechanisms. That was our target. So we have summarized this thing over here. You see that is there any vacant coordination site at all or not? Okay, if there is no dissociation, the Y group from the chromium side or the B metal side, then there is no possibility. One vacant site has to be created, otherwise it will become 7 coordinated, which is not a very stable or likely situation. Then is there a substitutionally labile reactant? That is very important. No? That Y has to leave the coordination sphere of one of the metal fragments. Has the ligand transferred occurred? Okay. Are there large difference in rate on addition or substitution of potentially bridging ligand? These are the factors one needs to question it. Now, what will happen that whether inner sphere or outer sphere, you can decide based on the kind of bridge you are using. For example, you see that you are using one particular oxidant. The same oxidant what you are talking about, na? Pentamine, cobalt, and X. Okay. Now, as a matter of X, you are using essentially the two. One is the azide one. You see the azide triple N. And other one you are using essentially isothiocyanate or thiocyanate. Okay. Now, if you use this one, that chromium, hexaco, vanadium, hexaco, all these things. Now, if you compare the rate, azide versus thiocyanate rate. Okay. Now, what happened that if the azide rate is much larger than the thiocyanate rate under a particular set of oxidant and reductant, that means the reaction is following the inner sphere mechanism. Why it is so? Because of this azide, you see that faster electron transfer takes place because of the symmetric nature. That means both the participating metal ions having the same donor site, right? On the other hand, if you consider the NCS, okay, then one metal unit linked to the bridge by the nitrogen donor, another metal unit which is linked to the bridge, same bridge by the sulfur donor. And because of asymmetric bridging mode or donating mode of the bridge, which reduces the electron transfer rate. Okay, so this prefers very strongly the electron transfer rate, makes it very fast, and this slows down the electron transfer rate. Now, if you have a particular set of oxidant and reductant and do the electron transfer, determine the electron transfer rate, this is small scale, electron transfer rate by using azide and thiocyanate, and if the ratio is too large, that means it is inner sphere. So in this case, what is happening, ratio is somewhere only 27, 2.7 or 0.27 into 10 to the power 2. So it is intermediate. Some amount of inner sphere, some amount of outer sphere, as we have shown one example previously with the ACAC compound. And in iron case, it is 10 to the power 3, naturally inner sphere. And in this case also naturally inner sphere. But in this case, it is outer sphere. Why outer sphere? You should answer it. Why it is outer sphere? It is outer sphere because of the fact there is no labile group over here. That means you have to create a vacancy over here. Now, otherwise it will be chromium. If X attached to chromium, it will be 7 coordinated. But bipyridine is a chelated ligand. It's not a monodental ligand. So if one bipyridyl leaves, and bipyridyl is a chelated ligand, it binds to the metal and very strongly. So it will not leave so easily. So as a result, it won't allow to form the bridging compound. If it doesn't allow to form the bridging compound, then on what way we should expect to have the inner sphere mechanism? And it is being very nicely reflected in the ratio of this. Okay, so both the processes having the same rate basically, and that means it is outer sphere. Okay, so this is how there are ways to figure it out. how to differentiate between the inner sphere and outer sphere. Though apparently, if we follow outer sphere, inner sphere together, you may have the immediate impression that there is a very subtle difference. My opinion is not. It's not a subtle difference. Difference is, quite substantial. But the problem is there are, say 80% cases, it's a crystal clear situation. Say inner sphere or outer sphere. If your luck is bad, that you are dealing one particular situation which does not fall to that 80% extreme cases. Okay. Unfortunately, if your compound follows the intermittent at 20%, where you see that it is neither inner nor outer, it is somehow at the borderline situation, and there you need to do all sort of control reactions, and then you can make some conclusion. And here it is a very crystal clear situation. Here. But this is also, one could argue, that is the outer sphere. I would suggest not the outer sphere. I would prefer to follow this particular slide, what we have talked about. Yeah, that a kind of mixed situation. Ratio might be different. That, if you could characterize or isolate the intermediates and structurally characterize, probably then we would be in a position to say in a much better way that what percentage of outer sphere and what percentage of inner sphere. Otherwise, we should say it's a mixed situation. I think that's all. Okay, I must stop here, and Thursday we will have a class, and then Monday we will have our your quiz, and subsequently we will have few more lectures and NSEM. Wish you all the best. Enjoy.
Sir,
Thank you, sir.
Yeah.
doubt from previous back lecture.
Hello.
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 Sir, doubt from back lecture.
Which one?
That microstate D2.
Microstate.
Yes, sir.
It's too bad. Why you did not raise it earlier? Yeah. What is the problem?
Yes, sir. I didn't understand that. How did you arrange the terms in star, double star, and dagger? How they were arranged?
Which one?
In the
Here.
table, how? No, sir. Up. D2 table.
Yeah.
Yes, sir. How did you arrange the terms in star, double star, and dagger?
No. You see that if you take one particular item, for example, +4, +4 means G, right?
Yes, sir.
Okay. ML plus, this is S, this is L. ML +4 means G. Okay. And your under G, S equal to 1 is not active. S equal to -1 is not active because of the Pauli exclusion principle. But S equal to 0 is active, right? Because you have a term over here, this block. That means your term would be 1G, right? This is
Yes,
active,
sir.
means 1, 2S plus 1, 1G. If it is 1G, then how many microstate would be there? 1 into 2 into 4 plus 1, 9 terms.
Yes,
Am I
sir.
right?
Yes,
2
sir.
ml plus 1 and 2 ms plus 1. So 9 terms you have to take it out. 9 terms means these are the 9 terms, this is the dagger. 9 terms I have taken it out.
No, sir.
Okay.
I was asking, why did you take that specifically? Those terms means in that 2 plus 1 minus.
No, it
that
doesn't
second.
matter. You can take the other one also. So this is symmetrically I have taken out.
Oh,
You
okay,
can-
sir.
We understood, I have
Yes.
taken out symmetrically. Otherwise, it will be a very confusing setup. Follow
Means
me?
the number of microstates only matter. The arrangement doesn't matter.
No, it matters because it has to be 4, it has to be 3, it has to be 2. This belongs to this particular row, That is important.
Yes, sir.
Okay. Now you could have taken this one. That is also 2, Right? 1 plus 1, 2, 2 plus 0 minus 0 is also 2, right?
Yes, sir.
Follow me.
Yes,
So
sir.
2 plus minus 0 equal to L equal to 2, and 1 plus 1, that is also L equal to 2. I have taken this one just to maintain some kind of harmony into the system. That you can take this one also, it doesn't matter.
Okay, sir.
So you have to maintain this part and this part, or this part and this part. Okay. So you take this one or that one, it does not matter. But overall, L and ML and MS has to be maintained.
Okay,
So
sir.
this, once you take 1G, this 9 term I have taken. Then 3F, I have taken this this star one, and so on and so forth. You follow it or not?
Yes, sir. Yes.
Okay. Then you just think a little bit quietly, and you'll see for your own understanding. Okay, we have taken a kind of symmetric pattern over here. You could have taken the other one. It doesn't matter. As long as ML and MS could be maintained, it's fine.
Okay. Okay, sir.
Okay.
Yes, sir. Okay.
Okay. Any other question?
No, sir. Not for now.
Okay. Okay. Anytime, feel free.
Yes, sir.
Okay. Thank you.
Thank you, sir.
Where is Deepika? She is here today. I cannot see. She must have left.